because my talk it involves the setting from both community detection domain and differential privacy. So I will talk about both some of the basic knowledge from the two domains, and then I will explain the center of the talk, which is presented in two of our papers. So the first one in ICML 22, when we have the first differentially private result for exact recovery. And the recent one in ICML 24, we extend the algorithm to work with other variant of the stochastic block models. So the basic task we talk about today is community detection. And in the context of network science, community detection is to detect subset of a graph that have strongly connected inside and loosely connected to other vertices. And there are many ways to detect such communities using metrics such as modularities or cuts. And the problem with using this metric to do community detection is you usually don't have the route choose community. So it's difficult to measure or to evaluate how well your algorithm designs. And one way to set up a benchmark system for community detection is to setting up some graph that has the underlying community structure in default. And stochastic block model is one of these models. Now, the vertices or the nodes in a graph are classified into different clusters. So each node I here will assign a value sigma star I that assign the cluster value for each for the vertex I. And the connection between all pair vertices are randomly sampled with some probability. So here is one example. These two pair vertices, they have the same label plus one. So the connection between them will be randomly generated with probability P, similar to this pair. But for this pair vertices, they belong to different communities. So the connection between them will be generated with probability Q. And P and Q are called intra and inter-communities probability. So the binary symmetric SBM is the simplest variant of the in the family of SBM. When we have equal sign communities, and there are only two communities in this simplest form here. So for the community detection problem in the binary symmetric SBM, the input is a graph generated by some SBM process here. And we want to output some vector sigma. And now the vector sigma is in the same form like sigma star. And we want to compare sigma and sigma star. When the two vectors, match up exactly, we call it exact recovery. And when only some constant fraction of the vector sigma match with the route to sigma star, we call it quick recovery for some constant rho. And in the non-private setting, there are several algorithms can perform the exact recovery, and I will highlight it. Exact recovery with high probability. So you can see that the algorithm only takes a random graph here, but the high probability statement is all over the process of SBM. So it's like you give me 1,000 graphs generated by the SBM. The algorithm will exactly calculate the graph choose for like 999 graphs. So the probability is over the state of the SBM, not the input graph. Okay, so are we clear about the SBM and the exact recovery problem here? Please stop me if you have any question, and I can, explain in more detail if needed. So the recoverability problem is a classic problem, and it had a long history of many works on this topic. So the first SBM was proposed in 1983, and for many years, people figure out the exact recovery and try to improvement on the recovery threshold. And only in 2014, the first type information-theoretic threshold has been proposed, and this is very important result. It states that the exact recovery is possible in the dense regime when P and Q are in order of log n over n for some constant A and B here. And it's only possible when there is some difference between A and B. And
so Jung,
yes.
is it natural log here in P and Q?
Yes, it's natural
Okay.
log.
Okay.
Yes. And they prove that when this condition is not satisfied, no algorithm can recover the graph to sigma star with high probability. And this is very important result. And the first algorithm to work to produce this result is the minimum bisection cut. So basically, you cut the graph into two equal halves. The algorithm is kind of a classic algorithm, but only when only in 2014 we can prove that the boundary here is tight. And of course, we have the efficient algorithm to solve it by using semi-definite program relaxation to relax the minimum bisection problem and solve the problem efficiently. So there are several other variants of the SBM, and this is the asymmetric when we have two unequal communities. We have the variant when we have the label for the edges of the graph, and we have the variant when we have multiple communities, and even some outlier vertices who which do not belong to any communities. And I will talk about some of the aspects of the other variant in the later part of the talk. So this is some basic thing about community detection in the context of stochastic block model. Now I move to the privacy part of the work. So you know, like nowadays, a lot of sensitive data was out there, and people have proved that there's many ways to retrieve the sensitive data from the public data set. And even when the public data sets were under some random perturbation or some kind of anonymized technique, we can still retrieve some hidden sensitive information. And in the context of graph, they can successfully retrieve the link or the connection between vertices, given that the graph is processed privately. And there are many privacy framework has been proposed to protect the privacy. And this is a partial set of the technique, but differential privacy is an important, and now this is a practical and theoretical tools to solve to protect privacy in many different settings. This is it appears in the executive order as one of the proposed techniques to be standardized in both industry and for government. Formally, differential privacy is defined as follows. We have a random algorithm M, and it's called epsilon delta differentially private. If given any subset O, and for any pair of neighbor X and X prime that differ by only one element, the probability of Mx belong to O is bounded by epsilon e to the epsilon times the probability Mx prime belong to O plus delta. The takeaway here, there are two things. The neighborhood definition again X prime, it depends on the setting and the domain. And the constant epsilon delta, we want some small constant epsilon and delta. And smaller epsilon and delta guarantee a better privacy protection. Of course, when we get small epsilon and delta, we degrade the utility of the problem. So if we want to have good privacy and good utility, that's usually a difficult task to do. So in context of graph, there are several ways to define the neighborhood between two data sets, basically between two graphs. And the model I use in this talk is the edge privacy. Basically, two graphs differ by exact one edge. There are several other model of privacy in graph. We have node privacy, which is two neighbor graph differ by one node, and order is adjacent edge. Usually, node privacy is very difficult to achieve, and some problem, for example, the community detection problem, only feasible in the edge privacy model. So the remaining part of the talk, I will assume the edge privacy model. So this is what we see, and this is what the private algorithm see. We only know the identity of the nodes and the public data, but the private algorithm can access to both the nodes and the edges. So we don't know the edge, but we know the nodes. And in the form of the output, we will output some group, some set of the node as a community. For example, I say that the two vertices here belong to the first community, and the remaining vertices belong to the second communities. That's the form of the output. So other than community detection, people do a bunch of other algorithms with privacy. And some of the problem, as I said, only feasible in the edge privacy model, which is the second big bullet here. When we try to output some structure of the graph, it's only feasible in the edge privacy, because if we output a node, we cannot use a node privacy model. And for other type of problem, it can be done in both node and edge privacy. So this is the context about differential privacy and some setting about the privacy model. Anyone have a question about the privacy models we use in this problem? Please let me know if you have any question, because I reserved some slides to explain about the privacy model if you still not clear about the privacy model here. So I will skip some slides and talk about the community detection, especially the exact recovery problem under SBM with differential privacy. Then I will try to explain about the semi-definite program. That's a way to solve the exact recovery in both the non-private and private settings. And then I will explain how it fits into a privacy preserving algorithm, and how we analyze the private algorithm to achieve exact recovery. So the goal we want to do is we want to design a private algorithm that we output a vector in the form of -1 and +1. It's a n-dimensional vector here. And we want the algorithm to be epsilon delta private, with any constant epsilon and delta. And we want to guarantee the exact recovery statement that if the input graph is randomly sampled from an SBM with some hidden ground truth vector sigma star, we guarantee that the probability we fail to output the ground truth vector is upper bounded by little o of 1. And specifically in this talk, I use the inverse polynomial n to the some inverse polynomial here of n. And again, the exact recovery statement, the probability space is over the randomness of the SBM. So this one is the statement here is high probability within this SBM randomness, and the algorithm is always differentially private. So you give me a fixed input graph, I guarantee you that the output is differentially private for any input graph. So here is some of the results we have in the ICML 22 paper. The column here is the algorithm. We propose several algorithms to solve the exact recovery problem. And the property in the leftmost column here is the range of the parameter that the algorithm can take, and the recoverability threshold, and also the running time. So among all of the algorithms we propose, some of them run with exponential runtime, some of them is polynomial runtime. Some only work with a special regime of epsilon, like the Bayesian only work with epsilon is order of log over b. All the rightmost here is only work with epsilon is order of log n. So among all of these one, the ones that has like many checkmark for it is the semi-definite programming using the stability mechanism. It can run with arbitrary small epsilon. It can run a little bit faster than the exponential algorithm, and it has really nice and clean form of the recoverability threshold here. So we will focus on the semi-definite program in this part. But again, there are several ways we propose that can also solve the problem. So in the ICML24 paper, we extend the framework to solve other variant of the SBM. In the previous slide, I showed the result for the symmetric SBM when all of the community have the same size. But in the extension version, we work with other variant of the SBM. The asymmetric one, the sensor binary when we have the label for the edge, and the general structure when we have multiple communities and some outliers. So that's some of the result and the problem statement, and some of the characteristic of the algorithm. Next, I will explain how the semi-definite program can be used to solve the exact recovery problem. So this is the semi-definite program, and it comes from a relaxation of the minimum bisection count. So the matrix A here is the adjacency matrix of the input graph, and the variable we optimize on is Z. So in short, C is a symmetric matrix that indicate something like if Jij equal to 1, then node I and node J belong to the same community. And Jij equal Zij equal to 0 denote that they node I and node J belong to different cluster or different communities. So just now use this semi-definite program as a platform. This program guaranteed to output the minimum bisection count of the input graph G, and we will analyze this semi-definite program for the exact recovery problem. Of course, here the form of the variable Z is a little bit different from the sigma star that I described earlier, but you can calculate Z star from sigma star. And basically, this is for the convenience when we extend the result to multiple communities, but their meaning is still are still the same. So Hyde et al. They prove an important result for the non-private settings. They provide a certificate, and you can think of it like if you can satisfy this condition for the certificate, basically meet all of the inequality here. Then the SDP, the semi-definite program here, will output the Z star, the ground truth matrix, as the unique for optimal solution for the SDP. And we can just use this result as a black box. And this will be very important to the talk. So this certificate here guarantees that the SDP output the ground truth as the optimal solution and the unique optimal solution. And
so, Dung, in the previous slide, the main equation for S star, right? I mean, the symbol connecting, the next slide, please. Yeah, in the main equation for S star, the symbol is the positive semi-definite symbol, right? It's come out a little bit differently. I just wanted to make sure it's not something else.
So this is, you asked about this symbol.
Yeah. The right on the right hand side, it's the positive semi-definite symbol, right? It's a little different from usual.
Oh, okay. I think I make a mistake when I use
Yeah.
the
Okay. I see. Okay. All right. Thanks.
curly size here. Yes, it means that the magic S star will be positive
So,
semi-definite.
yeah. Okay.
Yes. And in order to prove the certificate, the most important thing is to construct the magic S star here and prove that S star will be positive semi-definite. And the remaining condition kind of easier to construct, but the most difficult thing is this one. So I put it into a different line here. So in the non-private setting, they can prove that with high probability, we can construct the certificate in the last slide. And we will use that result as a black box, but we will modify that approach a little bit to apply it to some special mechanism called stability mechanism. So this is a general mechanism in differential privacy. So we define the stability as a distance from a data set to the nearest unstable neighbor. So we call a graph k-stable if we flipping up to k connection of the input graph G and still doesn't change the output of some function f. So which means that for if a graph is k-stable, then any neighbor within distance of k will have the same output of f like this equality here. So when k equals 0, which means that when you change one edge of the graph and the output of function f change, we call that graph is unstable. So we will calculate the distance. Here is a mechanism. The mechanism is we calculate for an input graph G, we calculate the shortest distance to some unstable graph from G. So I will let you know how to calculate that distance. But just assume that we have that distance and we call it df of G here. We add some Laplacian noise with the magnitude over of 1 over epsilon. And I will explain later that how it fits to the context here. But just now think of it like a black box that you have a noisy distance to the f of G here. So if the noisy distance larger than some threshold here, we output the output of fg, and otherwise we release a random output. So this is the mechanism, the stability mechanism, and the privacy comes with a mechanism. So basically, you plug any input graph G or any function f into this mechanism, it's still epsilon delta differentially private. So the privacy guarantee comes with the mechanism, and we can just use this as a black box. The difficult thing is, does this mechanism provide exact recovery? And we need to analyze it. And this is the center of the work, because it's much more difficult to guarantee the utility than the privacy in this specific mechanism. So the idea is, if df of G is in order of log n, then by using the property of Laplacian distribution, this noisy distance d tilde df of G will be always larger than the threshold on the right hand side here. So if df of G equal to some order of log n, then with probability, with high probability, we will release fg. So the idea is we will prove that the input graph G is log n stable under some semi-definite programming, and then the stability will take care of all the other property. That's the main idea. So in order to prove the log n stable of graph G, we construct a concept called C concentration. So C concentration is a set of collection, is a collection of conditions like C1 to C4 here. For example, we say that a graph is C concentrated if it satisfies all these four conditions here, such as, for example, the condition C1 is the number of in-community neighbor minus the number of out-community neighbor of a node I is not too small. Or the adjacency matrix A, and you can think of A as a random variable. So A is not too far from its expectation. That's the second condition. And we will prove that three things. So these are three statements we will prove. The first one is the C concentration. It will happen with high probability. The second thing is the concentration here remain invariant under block and edge flipping. So you flip block and edges of the input graph, and it's still C concentrated. And the last thing is we will construct the certificate we see in earlier slides using the condition from the C concentration here. And then from three statements here, we go to the theorem that G is log n stable under SDV with high probability. So this is a high level of what we will go into detail in the next couple of slides. Is there any questions about C concentration? Okay, so this is how we formalize C concentration. So for example, here C1, we define Si as a number of in-community neighbor of a node I, and Ri is the number of out-community neighbor of a node I. So all the statement here is designed in a way that it can be extended to multiple communities. But first, let's see in the case we have two equal communities first. So this is how we define all four conditions formally. And what we have to do is we use all four conditions here to do three things in the previous slide, the three statements here. So first, we will prove that concentration remains unchanged even if you flip log n number of edges. So for example, the condition C1. Condition C1 says that the differences between Si and Ri always larger than some C1 log n for some constant C1. So what happens if you flip log n edges of the input graph? You either increase this a little bit or decrease it a little bit. But again, you don't change the differences here more than some log n value, right? So the first condition remain unchanged even so we may have to change the constant here a little bit, but it's still true for some constant, right? So we now prove that this first condition C1 doesn't change under log n edge flipping, and all other conditions C1, C2, C4, C3, we do the same thing. We change up to log n edges, and we measure how these quantity change, and we guarantee that it still remains the same, although the constant may change a little bit. So that's the first statement. We prove that the concentration remain unchanged under log n edge flipping. The next thing is we prove that concentration, C concentration, happen with high probability. So basically, we prove each statement with high probability and using the union bound for the whole set of statement. But let's see the first condition C1. So C1, we say that the differences between Si and Ri is larger than C1 log n for some C1 constant. So we notice that S1 will has a form of a binomial distribution with two parameters. We have n over 2 possible connection, right? And each connection has a probability of a log n over n, because S1, SI here is the number of in-community neighbors. Similarly for Ri, we have similar thing, but the probability of a connection in Ri will be d log n over n, as we defined in the beginning of the talk. So we can use the tail bound between of the differences between two binomial random variables to prove that the differences between Si and Ri is lower bounded by some constant C1 times log n. Similarly, we have the quantity here, which is the number of cross community edge between two communities. We have n over 2 squared number of possible edges between two communities, right? And each of them have the probability Q. So this one can be proved easy by using Chernoff bound. So we do this similarly for other condition, and using union bound, we guarantee that concentration all four conditions happen with high probability. And the last step is when we have the concentration, we will prove that deterministically, which means with probability 1, we can construct a certificate for the SDP. And recall that when the certificate happens, the SDP will output the ground truth as the optimal solution. So come back to the certificate. We need to construct this version S star here. And S star will be positive semi-definite. So how do we do that? We prove that basically in very high level, we prove that this quadratic form of S star here is larger than 0 when n is large enough. So by the definition of S star, we expand the equality into this one. And as you can see, this quantity here, the quadratic form of A minus expectation of A, we prove that this is lower bounded by the second condition. Let me go back to the second condition. Here's the second condition. We prove that the L2 norm of A minus E, expectation of A, is upper bounded by C2 square root of log n. And then we plug it into our inequality here. Now, temporarily, we can ignore this part, because this part, we can prove that we can set it up such a way that this quadratic form here equals to 0. And the remaining part is to prove this one here is large is equal to something and larger than something that I will talk about. So come back to the definition of D star. D star is this kind of this form matrix. It's a diagonal matrix that formed from Bi star here, with Bi star equal, not equal, but larger than 0. So conveniently, we set Bi star equal to this whole quantity here on the right hand side. And by using math, we get it into this part. When this is here, is the form of the third condition in C concentration. And again, this part here is we apply the first condition of the concentration. So we have that the minimum eigenvalue of D star to be at least this quantity, and therefore the quadratic form of D star here, take this one as the lower bound. So now we plug this result here to the inequality of S star. What we have remaining, we have this one here, the C1 log n factor here, and we have a bunch of square root of log n factor in the negative side. So basically, we have square root of log n here, and we have square root of log n here. So basically, when n is large enough, this quadratic form of S star, it is guaranteed to be larger than or equal to 0. So this is a part when we prove that S star is positive semi-definite. So this is there are many small details in proving the certificate, but this is the main part. And come back to the certificate, we guarantee the most important criteria here when we prove S star is positive semi-definite. So the last slide, we prove that with the concentration, we can construct the certificate. And when the certificate happens, the semi-definite program has the optimal solution as the Gaussian matrix. Now we also have proved in the previous slide that when you flip up to log and edges, the C concentration remains the same, which means that from a graph G, you go up to log and distance, all of them have the same concentration. All of them have the same certificate, which means all of them output the Gaussian as the optimal solution of the SPP, which means that you can add or remove up to log and edge to the graph, and the output of the SPP is still the same. So I can say that the graph G will be log n stable because I add up to log n edges and the output still the optimal solution. The optimal solution still the Gaussian vector. And the last, the first statement here, we prove that we can have the C concentration with high probability. So by the property of the stability mechanism, we guarantee that the stability mechanisms almost always produce the Gaussian and its solution. So this is how the final theorem look like. We construct the constant here and the condition here using the constant C1, C2, C3, and that related to epsilon. This is a bit tricky on how to do that, but this is how the final result about the recoverability threshold look like for the symmetric binary SBM. So I just
Zoom, can you go back? So you've assumed that n equals n to the minus t, right? So that's very good DP. So for example, if t is a positive constant, that's very good DP. But suppose we don't require that much, right? So suppose I say t equals 1 over square root log n is enough for me, right? So if t is just as an example, if t is like 1 over square root log n, then yeah. So my point is by making delta not go to 0 that fast. So my question is, this theorem, is it true for any parameter t, or does it require that t should be lower bounded by some positive constant?
So there are two things. It can be true for any t, but
okay.
They prefer delta to be smaller than 1 over n.
You require delta to be smaller than 1 over n?
Yes, that's the convention in differential privacy. There will be some situation when you lose privacy if you don't set delta small enough. In theory, it can happen. So this is the convention in differential privacy community to set delta equal to some inverse polynomial of n.
Okay. I see. And is it true that even in your specific case, if delta doesn't go to 0, like an inverse polynomial of n, for example, suppose it is, suppose it's going to 0, like 1 over 2 to the square root log n, for example, then there'll be some break basically maybe just by looking at the epsilon delta dp definition, you're able to show that for your specific problem for the stochastic block model, you can show that delta has to go to 0 like this, like n to the minus t?
No, it's generally true for any epsilon delta private mechanism. So delta must be smaller than 1 over n in many cases.
Okay, what I'm saying, yeah, my specific question is this, Jim. So suppose for your specific problem, you don't require delta to go to zero that fast. Maybe you do, maybe you do. So I think what you're saying is that for the general DP problem, you typically require delta to go to zero very fast, right?
Yes.
My point was, suppose you can show, maybe you cannot, maybe what I'm conjecturing is not true, but suppose you can show that for your specific problem, delta doesn't have to go to zero that fast. It still goes to zero with n, but suppose essentially what I'm saying is suppose t is an appropriate little o of one, right?
Yes.
But still there is the t plus one. It's not just t. So I see that there is the t plus one. If it were, what I was trying to say is that if the t plus one was instead just t, you can make both t little o of 1 and epsilon little o of 1 and still get a pretty good result. But okay, so but there is the t plus 1. Is the t plus 1 unavoidable? Can you replace the t plus 1 just by t?
No. I need the first one is when I take the union bound over all of the vertices. So it's always there.
I see. Okay. All right. Okay. Thanks. Yeah. Please proceed. Yeah.
Yes, so that is for the symmetric binary SBM. And we found a way to extend the problem to other variant of the SBM. But because each variant of the SBM have a different form of the semi-definite program. And they come with different certificate. So not many part of the analysis here can be directly applied to the other variant of the SBM. And also we need to construct a specific C concentration definition for each of the variant. So this is one example for the asymmetric SBM. You can see that even without privacy, the recovery threshold is much more complex than the symmetric state. So in symmetric state, you only have like square root of a minus square root of b is larger than square root of 2. Here you have complex inequality for the recoverability. And here is the form of the SDP for asymmetric compared to the symmetric. And I just want to show they have different form. And then this is what we have to do to construct C concentration for asymmetric. Basically, except for the first condition, it's very difficult to explain in normal language, human language. What's the meaning of the condition here? Unlike the symmetric case, when we can, at least explain what is the meaning of C concentration. Now it's too complicated and very difficult to explain it. But we still have a way to construct them, the C concentration here, and then we still prove the three statement, which is this concentration happen with high probability. These conditions are invariant under log n h flipping. And from this condition, we still construct the certificate for the SDP to be optimal at the ground truth. So this is a lot more work for the asymmetrics. And similarly for the sensor version, when we have the H label and for the general structure of the SBM. So I don't want to go over all of these details, but this is the result. This is how the recovery threshold look like for other variant. Basically, seems a bit messy, but this is the result. So for other variant. So in conclusion, I just described how we use differentially private algorithms to achieve exact recovery for different variants of the SBM. We prove it using the concept of C concentration and using the stability analysis framework to construct the dual certificate. So there are several open questions we are considering. Is we just prove the upper bound side of the problem, which means when the condition happens, we can do exact recovery. We don't know if there is a lower bound for differentially private algorithm, which means that with a fixed epsilon and delta, what condition in which we cannot do the exact recovery? We don't know it yet. Although the result the newest result I have here, you can see that when epsilon go to infinity, which means we have less privacy and more accuracy, the threshold we have is close to the non-private setting. So which is a hint that we are very close to the lower bound, but we don't know if the lower bound exists or not. And second, we are trying to expand this framework to solve other variants of the SBM. For example, the one where we have overlapping communities or the power law SBM. So it better model real life network. There are several other type of SBM that people are considering in the literature. And we are trying to see if the framework here can expand to other variants. Okay, so basically that all of the thing I want to present today, and thank you very much. And if you have any question, I'm happy to answer it.
So I didn't understand the dual certificate stuff. So I'm not. Are you able to write on your laptop? So can you show something about the dual certificate? I know SDP duality at a high level, but what exactly of the dual are you using?
So I only use it as a black box, and I don't go into the detail in our work. And I forget some of the detail about how this certificate leads to the optimal solution, but I can get it back to you offline by email.
Okay. And I have a question about the original, the classic research by this is Emmanuel Abbé, right? From Princeton? ABBE, Emmanuel, when you showed your the original results on non-private, recovery by Abbé, ABBE. That's Emmanuel Abbé, right? At Princeton?
Yes, that's
Yeah, and Hayek, yeah. Yeah, so when you look at their, for example, what's the high level idea behind, so you're saying the algorithms due to Hayek et al. Are SDP based algorithms, okay? And the information theoretic results by Abbé et al., right? So, can you give some high level idea what the upper bound and lower bound ideas here are? The square root. Mhm.
So the upper bound in the Abbé paper, they use the minimum bisection cut. So basically, the just the cut that divides the graph into two equal half. The algorithm is still basically the SDP is just a relaxation of that minimum bisection cut.
Yes.
But they use so basically you can calculate the size of the cut, right? This is a tail bound of two binomial distribution, right? And using that tail bound of two binomial distribution, you can derive the upper bound. You see what I mean?
Okay. And what about the lower bound?
With high probability, the size of the cut, which we can represent as the difference between two binomial distribution, is larger than some amount with high probability, and that will be used for the upper bound. For the lower bound, I forget how they did, but I think what they do is they encode the SBM as a series of communication channel, and they prove that the capacity of the channel cannot encode the number of edges when the condition square root of a minus square root of b is smaller than square root of 2. So that reach the maximum amount, the capacity of the communication channel. But
basically you're saying that there is no unique row that matches row star, right? There can be multiple rows. Is that the reason? When A and B are too close to each other, maybe there are many choices of bisections, which which statistically satisfy the inside cluster and outside cluster number of edges. So you can't. There is no unique row that satisfies the sigma that satisfies sigma that equals sigma star. Is that part of the intuition?
Yes, that's part of the intuition.
Okay, I personally don't have other questions. So.
I think one of the conditions of the algorithm was requiring that like the number of neighbors from the same community you get minus the largest other community neighbors, right? Is not too large. What's the intuition behind wanting to minimize this quantity?
So, what happens if you don't have that? Is when you have one vertex that have more out community neighbor than the neighbor from its own community, right? That's the inverse of the statement. When it happens, then you will miscorrectly assign that vertex to other community than its true community. So when it happens, we cannot exactly recover the ground truth. So the C concentration represents a well-behaved graph when it doesn't have that situation. Because when it has that situation, for example, you belong to the first community, but you have more friends in the second community, then any algorithm should give you in the second community. And because of that reason, you cannot retrieve your correct ground truth community. So in order for a graph to be well behaved, then it must follow all of the conditions. And that's the intuition for the number of in-community neighbor must be larger than the number of out-community neighbor for any vertex size.
In practice, I would imagine like people like this do exist, right? So is there any work considering maybe like some budget of nodes that may have this property that you can either eliminate or something like that?
Yes. So that people study in the other variant of the exact of the recovery. So this is the weak recovery definition when only some constant fraction of the vertices can be recovered with exact community status. So it allows for one minus row and vertices to be incorrectly classified into community. And it's a little bit different problem than the exact recovery. But again, this is an interesting problem, and people study that quite a lot. The weak recovery problem.
Any other questions from the audience?
I have a question about the result on like multiple different structures. I wonder what are the size constraint for communities there.
So yes, we do have the size constraint. So all of the so for example, in this variant we have R community, and all of them are proportional to some constant rho R. So the size of the community will be the ratio between them are always some constant. So they grow together linearly.
So it's still like it doesn't extend to arbitrary community size.
You still always have to set up some model for that. Arbitrary seems like unit. So again, there's many variants of the SBM, and I think in some variant of SBM they have the size of the community doesn't grow uniformly, right? That's a different variant, and we didn't consider that type of SBM model in these papers. But yes, it exists.
Thank you.
Any other questions? Okay, let's thank Dung very much again for visiting. Dung, write to me once you're back. Let's talk more about the directions we spoke about.
Yes, thank you, Arabin, for inviting me here, and thank also
Thanks, folks.
for showing me around.
You're very welcome. Thanks.